of one of the talks. Each talk is 5 minutes plus about 2 minutes for questions. And then feel free to ask any questions you have during any presentation on Slack, and we'll make sure to ask the authors when they're done with their presentations. Having said that, I think we should jump right in and get started. The first talk is CPS Debug, a tool for failure explanation. The talk will be given by Nivedita. Welcome, Nivedita.
Thank you. Yeah, so I guess I will start with just sharing the screen immediately, and then presenting it. Okay, I'm sorry, do you clearly see my screen and hear my voice?
I do.
Okay, thank you. So hello everyone, I will be presenting CPS Debug. I'm Nivedita as the chair introduced. So yeah, I mean, cyber-physical systems are complex network systems. They are everywhere. It could be such as autonomous vehicles, or it could be smart buildings, for example. And these are extremely difficult to design and verify because of their continuous and discrete dynamics, of course. Now, even after detecting the fault, it is challenging to understand when and where these faults occur and also why. Now, we present CPS Debug, which is a tool that supports an engineer to localize and explain failures in CPS, given a Simulink or state flow model. So we assume that we are given a system under test, a test suite, or maybe I should use the pointer. Yeah. Okay, so we assume that we are given a system under test, a test suite, and a set of requirements written in signal temporal logic. Now, signal temporal logic is a requirements language that can be used to describe specifications for hybrid systems or cyber-physical systems. Now, we input to the tool this system under test, test suite, and the specification. And the tool outputs as failure explanations, a sequence of snapshots that provides an explanation of where and why the failure has occurred. Now, how do we do it? So we first instrument the system under test, and then we simulate this instrumented model, and then we record the internal behavior of the system. Now, some of these tests might pass and some might fail based on the specification. So from the past test, we infer invariance over continuous, over dynamic traces that that capture the continuous behavior, and then we also infer timed automata that captures the discrete and timing behavior of the system. Now we use this information. So whatever we have captured in this form is actually capturing how the system behaves when we satisfy the specification. Of course, this is then used to detect and localize components in time and space where anomalies occur. Now, some of these learned specifications or the properties may pass on this fail test, or some may also fail on these fail tests. Now, each of this invariant or the timed automata that has been inferred represents the good behavior of some of the internal components of the system under test. Now, a failure of each of these monitors that has been inferred from the fail test indicates that there is an anomalous component or anomalous behavior in any of the components that has failed. Now, we capture also the time at which these violations first occur. So then we cluster these violations that has occurred, and then according to the time of their occurrence, we create this sequence of snapshots that is again mapped back into the model. And we see how or where in the model this failure has occurred. Now, I can just show you a small demo of how we actually run this tool. So first, we set the path, we open MATLAB, and then we set the path to the tool. And in the configuration folder of this tool or the path, we set the signal temporal logic specifications that describe the behavior of the model. And then we also have a configuration file where we set the path to the model, the specification file, a test suite, and constants and thresholds if the model requires any. And then in the command window over here, we give the command CPS debug, and then we pass the arguments also that is the configuration file and the path to the results. Now, once we run this tool and it's executed, then there is this path where we've already said we want the results, and in this folder we have the explanation of every failed test. Now, each of this failed test contains an explanation such that the component that has failed and the place in which, or the block in which this is, and the violation time that it has occurred. Now, this, as I said, can be mapped back into the model. And then in the model, you can see which of these blocks actually were violating our specification or the good behavior that has been inferred by the model. And this is visible on the model itself. The mapping back of this with respect to the clusters is so this is done manually, and in future we would like to also have this automatically. Yeah, that is what I would like to present. Thank you.
Thank you very much for the talk. Are there any questions from those who are listening? If there are no questions, I just wanted to ask, what is an example of a failure here that you're trying to explain?
So the violation of a specification. Here, for example, we could have some invariants that are such as something over continuous traces. Mm-hmm. And then it's possible that we have a violation that says, okay, you have this single trace that goes beyond the bounds of what is expected for the given trace.
So you find that violation when the failed tests are run? Yes. Is that the case? Okay. So yes. Your assumption here
once
is
the test is run, once we obtain the failed test, and then we see, we use the monitors on the failed test, and in the failed test, we can detect which of these components. So for example, if you have one of this being violated, then we say, okay, you know, the omega-1 is actually going beyond this value, and we can actually quantify this as to how far away we are from violating the specification, or having been violating the specification, or even with respect to the timing, or as to how far before or how far after this value should have changed.
Okay. The other question I had was, is it always the case that when a test fails, it's because one of those invariants that you mined were violated?
Yes, because it is one of these invariants that are being used to monitor these traces, and we capture the behavior. So,
but the test could fail independently of your monitoring.
No, it has to fail only with respect to one of these invariants, because these are the new specifications for the model for us.
Oh, you're saying your tests do not come with their own assertions or specifications?
No, the test by itself does not come with its own assertions. It comes with this overall specification, which says at a high level, this is how my system should behave.
Okay.
And then at the next level, we infer our own properties from the internal behavior of the system. So basically, we are trying to understand how every single component behaves inside the system using past tests, which means this is like a subset of the behavior that has been inferred. And then this subset of the behavior is actually being used to explain the failures from the failed test.
Okay. Okay.
Yeah. Thank you.
Well, thanks for your talk. Let's move on to the next presenter. The next talk is crowdsourced requirements generation for automatic testing via knowledge graph, to be presented by Chao.
Oh, okay. Can you hear me?
Yes, I hear you.
Oh, okay. Hi, everyone. This title is Crowdsourced Requirements Generation via Knowledge Graph Construction on Automatic Testing. Android applications occupy the most of the mobile application market due to the diversity of Android platform brands and Android system versions. The fragmentation of Android system is becoming increasingly severe. Various application scenarios and the frequent iteration cycles make Android testing difficult. More and more developers solve the dilemma facing Android testing by using automatic testing and cloud testing. Android automatic testing can detect presentation errors or exceptions, which can be called suspicious bugs. It is unclear the impact of suspicious bugs on the application of automatic testing. In the traditional crowdsourced testing process, CloudWorks follow the introduction in the test requirements to complete the test task. However, manual generating test requirements is tedious for the requesters, who should gather domain knowledge of the target application. In order to solve the problem of requirements generation, we have developed the Kara. Kara first analyzed the result of Android automatic testing on the target application to obtain window transition. Then, Kara constructed the green model for the target application. The Declarative algorithm is adapted to calculate the shortest operation sequence from the application start interface to the suspicious bugs interface. In the meanwhile, the static analysis technology is utilized to get widget information from the source code. Based on the result of static analysis and the transition information of the green model, Kara constructs a knowledge graph. Ultimately, Kara combines the shortest operation screen with the knowledge graph to generate the cloud test requirements so that CloudWorks can reproduce the suspicious bugs of the test requirements. The requirement includes 4 parts. Firstly, test environment information, which include the information of application name, application version, device brand, and the network condition. Secondly, suspicious bugs information, which contains of the log information and a screenshot of the suspicious bugs. Thirdly, the requirement step list, which contains the operation description of each step. It clearly defines the Windows transition and hints for the next transition windows. Lastly, screenshot list, which include a series of screenshots of the step. Kara can generate cloud testing requirements automatically. Requesters can obtain effective requirements from Kara quickly. Besides, CloudWorks can reproduce suspicious bugs easily according to the requirement generated by Kara. We conduct experiments to address the 2 research questions. The first is, how understandable does Kara generate the test requirements? We design a simple and conduct a survey to collect the certification of 20 participants on the comprehensive ability of the test requirements generated by Kara. We found 19% of participants had a positive attitude towards the understandability of the test requirements. The second is whether the test requirements generated by Kara effectively improve the qualities of crowdsourced testing. We conduct a control experiment. 20 experiments were divided into 2 groups that test the application on the device. Group A is a control group that tests by themselves. Group B is the experimental group that tests applications according to the test requirements generated by Kara. Within 2 hours, effective bugs would account for 57.6% and 18.9% in Group A and Group B, respectively. We can find that the test requirements generated by Kara can effectively improve the quality of crowdsourced testing. Okay, thank you.
Thank you for the talk. Let me pause for a little bit to see if there are any questions from the audience.
Okay.
Does anybody want to ask any question? Okay, if there is no question, then I will ask. So you showed a table comparing the crowdsourced. Can you show your table again?
Okay. This table?
Yeah, so in your controlled experiment, who were the people who partook here?
The 20 participants is sorry, okay, this is the 20 participants are graduate students majoring in software engineering and have been registered on the mock test platform for more than 1 year.
Okay.
They have okay.
Okay. Okay.
Thank you.
Yeah, in the interest of time, I want to move this along. So thank you for giving that talk. Let's go to the next presentation. Wentian will tell us about the work, the tool, eShield, protecting smart contracts against reverse engineering.
Can you hear me?
Yes, I can hear you.
Okay. Hello, everyone. My name is Wentian Yan. I'm currently a master's student from Peking University in China. Today, I will introduce an anti-reverse tool for protecting smart contracts against reverse engineering. In recent years, Ethereum smart contracts are widely adopted, which covers so many areas. CryptoKitties is a popular Dapp in Ethereum that allows players to breed and trade digital kitties. A new kitty is created by splicing together 32-byte genomes from each of two parents. The kitties with rare genes may have higher value. For security reasons, the central component of the game code was kept opaque, but researchers used the reverse engineering tool to translate the bytecode and analyze the gene mixing functionality. Finally, they find some methods to create high-value kitties. That means the randomness of the game is broken, and it may lead to reduction in the value of kitties. So we want to find out some methods to make the reverse engineering more difficult. From the practical perspective, there are two main challenges. Firstly, the EVM does not follow the standard von Neumann architecture, and the code is stored in a virtual ROM. The code cannot be modified during execution, so we cannot execute encrypted code in Ethereum. Secondly, the existing anti-reverse engineering techniques, such as obfuscation, adding a large amount of extra instructions, and leads to a significant increase in gas cost, which makes it unacceptable to developers and users. To address the challenge, we developed eShield. The key insight behind eShield is to increase the difficulty of recovering CFG by interfering with identifying the connections between basic blocks. eShield takes runtime bytecodes as input and puts them into an analyzer. Then it recovers the CFG and detects the suitable position to insert the anti-patterns. The pattern constructor produces the anti-patterns with the obfuscated jump address. After that, the length of bytecode will increase, so the extra length will be transmitted from pattern constructor to original constructor. Then the original bytecode will be reconstructed and generate the modified bytecode. In the end, the bytecode constructor will insert the anti-patterns into the modified bytecodes and generate the protected bytecodes. eShield first use EVM CFG builder to recover the CFG of contract. The analyzer marks every jump high with their jump address and keeps them in jump pairs. Each jump pair consists of 4 attributes. First is the address of jump high. Second is the address of gem depth. Third, if the address of gem pi is ahead of the address of gem depth, it's called normal. If not, it's called reverse. Fourth is the length of jump address. The purpose of this step is to make sure the CFG of protected bytecode will be correct. At the same time, we mark every sequence of instructions, such as equal push jump pi. We take them as the entry of functions and replace the jump address with anti-patterns. Now let's follow pattern 1 and see how the method works. After a series calculation, we got the new jump address and we push the new address into stack. Then we push the offside of memory into stack. This offside will be used to store the value of jump address in memory. Now we have two values in stack and MSTORE. We use MSTORE to store the second value into memory, which the first value is its offside. Now we have to load the address out of the memory. First, we push the offside into stack. Then MLOAD will read the value which the offside in memory is 40, and the value of this offside will be loaded into stack. At last, the jump pi will read the top value of stack as the jump address and continue to execute the other instructions. In pattern 1, we use MSTORE and MLOAD to obfuscate the jump address. The other patterns' main idea is the same. The main difference is the way they deal with the jump address. In pattern 2, we use SSTORE and SLOAD. In pattern 3, we use SHA-3 to generate two identical hash values and divide them to get 1. Then we multiply the address and 1 to get the jump address. In pattern 4, we call an external contract and use the return value to produce the jump address. With the extra length and jump pair's original constructor, we modify the original bytecode. After all, it will insert the anti-patterns into the modified bytecode to generate the protected bytecode. We have deployed eShell as a web service. User can input the bytecode and select the folder paths of contract fields. Then 4 patterns can be selected. At last, click the blue button and the protected bytecode will be displayed in the blank or saved in fields. And we use Erase, Wonder, and Gigahertz as benchmarks. These tools are good reverse analysis tools of smart contracts. As shown in the table, all the 4 patterns can effectively fight against the reverse tools. On average, the extra cost of creating a contract protected by pattern 1 and 2 is less than 1 cent. And the extra cost of calling a contract protected by pattern 1 and 3 is less than 0.1 cent. The present work is to verify the effectiveness of the basic methods, and we plan to explore more complex methods and generalize the technique to other blockchain platforms. Thank you for listening.
Thanks a lot for that presentation. I have a question from people in the audience. How does this approach compare to using obfuscation tools? There are many obfuscation tools for Android, but is this the first obfuscation tool for EVM?
These tools just take the runtime bytecode as input and generate the CFG of the contract, and we compare each CFG or other formats of the result to compare the CFG is correct or not. If the CFG missing any blocks or generate a wrong answer or just generate nothing, then we take it as a fail result, and we take them as the fail case.
You've explained how you do this, but I guess the question being asked was, how does this compare to other kinds of obfuscation tools? So someone else is asking on Slack that, obfuscation has challenges in other domains. People have tried obfuscation before. What usually ends up happening is that when you obfuscate more strongly, people will de-obfuscate even more stronger. So what is it that makes blockchain different, and why do you think people will still not break your obfuscation?
Oh, I got it. And because the other obfuscation techniques use a lot of instructions and fill in the bytecode and make the bytecode more expensive because the contract used we execute in the EVM and may cost the user and developers some gas that makes the contract more expensive. So we cannot to insert more instructions in the smart contract, and so we want to find out some methods to insert as few as possible. The fewer instructions, the better the method works.
Yeah, so okay, you said that for basically in the case of EVM, what's the cost is a deterrent. So if they want to deobfuscate, then they need to spend more. That's I think that's the answer to the questions that Milosh and Darko asked. Okay, now thank you so much, Chao, for your question. We will then move on to the next talk, which is Echidna, I believe. Effective, usable, and fast fuzzing for smart contracts.
Yes, exactly. Can you see my screen?
Yes, I do.
Okay, thank you. So hello, I'm Gustavo Grieco, part of Trail of Bits, a company that do security audits. We published this tool, Echidna, for fuzzing smart contracts in collaboration with Northern Arizona University. So let's start. 1 minute introduction of what are smart contracts in Ethereum. So smart contracts are a piece of code that are deployed in the network. We can call this network the blockchain. Users interact with this smart contract through transactions, and this transaction usually carry some value in terms of funds like Ether or stable coins. So of course we want to make sure that the smart contracts are secure, are correct, and this usually means that you can test them in an effective way, right? Because they have code as other programs, and once you deploy, it's effectively there forever. There are ways to upgrade smart contracts, of course, but these are usually not recommended because it can produce more security issues. So usually the smart contracts are deployed forever, so you cannot patch it, right? So that's why we published 2 years ago one of the first open source smart contract fuzzers that you can download and use. It was implemented in Haskell using HAVM, which is an implementation from the AVM. It's focused. So Echidna will generate input transactions for your smart contract to test. But you need to give them what is called the ABI, and in more general, you need to give them the source code. This is not like a hard requirement, but we did it like that because we usually review a smart contract with source code. So we don't do reverse engineering on the audits that we perform. So the focus of Echidna is to have good results in short fuzzing campaigns, like a few minutes up to an hour, let's say. And it's also designed to be ready to use, to be easy to integrate with your continuous integration pipeline. We found that others open source smart contract fuzzers were difficult to use, difficult or impossible to use, and they were not maintained and not really practical to use because you have to download all the blockchain or deploy some in a simulated blockchain, and it was very slow to do it and very impractical. So a very simple example, we have this smart contract that has 2 operations. This is very artificial, but it will just be used for this demonstration. So in smart contract, you don't have any crash, you don't have any indication of a bug, so you need to manually add a property to test. So this is taken from property-based testing. In this case, we have an invariant that has two Boolean values. So Echidna will try to execute set0, set1 transactions, one after the other in a random way, and it will try to break the invariant. So we have the two invariants, one is trivially true and the other is it could fail. So if we run this, we will have that Echidna will find after a couple of minutes, after 50,000 simulated transaction, we'll find and we'll minimize the input, right? And you can see how you can. So as I said, in general, properties should be encoded. There's no easy way to have bugs in smart contracts unless you have them. So you can just code it as a Boolean function. And well, we don't have generic bug detectors. And well, the reason is like it can be too expensive to detect and to do the instrumentation, and we always have source code. Okay, so that's it. Any questions?
Thanks for the talk, Gustavo. Let me pause to see if someone is asking a question on Slack. I see someone typing. But meanwhile, you said that assertion checking is disabled by default. Can you say a bit more why you do that?
So sometimes the developers don't really understand what the keyword assert means, and they use it to enforce something that you should not do with your contract. Like, for instance, you should not send some input to 0. You should not set like some input value to 0. So they, instead of putting required, that is the usual way to do it in Solidity, they put assert, which is not correct, but it will work in the same way in practice. So we disable this because sometimes assertion checking is not actually checking anything useful, and you need to enable with the flag, and that will be enough to have this running.
Okay, thanks. So Milosh is asking a question on Slack. What are the key differences from existing fuzzing tools, and what do you think are the key challenges compared to, say, fuzzing C++ programs?
So yeah, there are so compare with other some of the other Fuzzer for smart contract are not open source, so we couldn't really compare it. We could compare with a commercial tool from another company that is supposed to be doing fuzzing and also symbolic execution. So Echidna will work better if you have short campaigns, right? It will give you a reasonable answer in a few minutes, right? And other tools will take more time. They will sometimes give you good answers, but they will take 20 minutes or so. And well, the evaluation for longer fuzzing campaigns, where we don't know, we can't say that we are better or not. And compared with other tools like AFL, there is a challenge with smart contract, and is that you need to do transactions. So you need to have one transaction after the other, and sometimes this is not straightforward for Fuzzer. This is really different from fuzzing a normal binary that has one input, and that's it.
Okay. Okay. Thanks for the talk and for your answers.
Okay.
Yeah. Thanks a lot. Let's move on then to the next talk. The next talk, Shuai, are you on the call? Okay, I don't, Shuai is not here. So maybe we can skip for now. I'll see if I can get Shuai on the call in a little bit. So let's.
There's a pre-recorded video. So.
Oh, okay. Okay.
Okay.
Hello, I'm Shao Shuai, and so glad to introduce our tool FunLock, automatically refactoring coarse-grained locks into fine-grained locks. Concurrent programs based on locks are susceptible to lock contention, which would result in low performance and poor scalability. Inappropriate grain of a lock makes lock contention even worse. It is generally accepted that a fine-grained lock may mitigate lock contention. However, writing a program based on fine-grained locks is much more difficult compared with that based on coarse-grained locks, which requires careful design and expertise. This inspires us to develop an automation tool to help developers refactor code by converting coarse-grained locks into fine-grained locks, with the hope of reducing lock contention. There shows a motivating example that extracted from Java API specification. The code shows a typical implementation of cache processing. The method is protected by a synchronized lock, which is a coarse-grained lock. It first checks whether the cache contains the date in line 2. If so, the date is read in line 5. Otherwise, date will be written into the cache. However, the write operation is executed only when the cache doesn't have the date. It can use lock downgrading to allow more concurrency. Here shows the code refactored by lock downgrading, which is a fine-grained lock. It first acquires a read lock, which is enough to ensure concurrency for the condition checking. When the condition holds, a write lock must be used, and thus the read lock is released, and a write lock is acquired. Note that the condition is rechecked in line 17 to guarantee the consistency, because the condition might be changed by another thread. After the date is written into the cache, the write lock is downgraded into a read lock. Then, the write lock is released. Finally, after the date is read, the read lock is released. The code indicates that when the cache has the date, the current thread only acquires the read lock instead of acquiring the write lock. It will get more concurrency. This is the design framework. The refactor prober is to locate synchronized locks that can be refactored into fine-grained locks, and summarize the statements in a critical section into a pattern. The pattern generator is to encode the sequence of programming statements into a sequence of characters, where each character marks the state of the statement. The pushdown automaton is utilized to infer locks based on a generated pattern for a critical section. Each character in the pattern sequence is used as a trigger to transfer from one state to another. FunLock conducts transformation on AXT by converting synchronized locks into re-entering read-write locks. We implement FunLock as an Eclipse plugin, so let's demonstrate the tool. First, select the project you want to refactor. Then click the tool. This is the refactoring preview. The left side shows the original code, and the right side shows the refactored results by using lock downgrading. The code is similar to the motivating example, so click the Finish button to accomplish the refactoring. We evaluate FunLock in 5 real-world applications. A total of 1,546 synchronized locks are refactored, of which 8% are converted to fine-grained locks. The size of the projects varies from 12,000 to 530,000 source lengths of code, and the time used to refactor each project is on average 27.6 seconds, which indicates fun lock is generally applicable to large projects. Funlock is available at this website. Thanks for watching.
Okay, I have to thank the authors, the presenters in absentia because they can't get in this Zoom discussion for some reason. That's unfortunate. What we'll do is then ask you to leave any questions you have on Slack. See if they can follow up at some point. Then we'll move on to the next talk.
Olalabi, we cannot hear you very well.
I see. Is it any better?
No, really.
Okay.
Now it's better.
Okay, I'm yelling now. So I was saying that the authors of the last paper could not be here to answer questions, so I'm going to move to the next talk, which is ObjSim, lightweight automatic patch prioritization via object similarity. Ali will give the presentation.
Thank you. Can you see my slides?
Yes, I do.
All right. Hello, everyone. My name is Ali Gambari, and I'm a PhD student at the University of Texas at Dallas. I'm presenting ObjSim, a lightweight automatic path prioritization based on the notion of object similarity. Automated program repair, or APR for short, is referred to as a set of automation techniques that, given a buggy program, can directly fix the bugs or help the developers during manual debugging. Generate and validate refers to a class of APR techniques that attempt to fix the bugs by generating a pool of program variants and checking the resulting variants against certain checks or tests to identify the ones that pass all the checks. Such program variants are marked as plausible fixes and are to be reported to the user for examination. Because of availability and practicality of test cases, most generate and validate APR techniques rely on test cases to validate the generated patches. However, test cases only partially specify the desired behavior of the system. And a patch that passes all the test cases doesn't mean that it satisfies the requirements of the software. Indeed, tens of the generated patches happen to pass all the test cases without actually fixing the bug. This deficiency of test cases is commonly known as weak specification problem. Therefore, test-based generate and validate APR techniques, in order to be practical, need a mechanism for post-processing their fix reports so that the user will spend less time examining their fix reports. ObjSim is a tool for patch prioritization, meaning that in a fix report, it prioritizes patches that are more likely to be cracked. The basic idea is to treat the behavior of the system on passing test cases as a partial specification of the desired behavior of the system and use it as a correctness criterion. In other words, a good patch is the one that not only doesn't break the existing passing test cases, but it also ends up in a state similar to that of the original program. Because on passing test cases, we want the patch to behave as similar to the original program as possible. At the same time, we want the patch to deviate from the original program on failing test cases to avoid non-erroneous states. Now, let's look into an example of fixing a Java program that, given a string str, an integer k and a character c, determines if c occurs in str at any index between 0 to k inclusive. For example, assuming that the name of the program is Finder, and we have instantiated the program with the following string, we expect the query for finding the question mark between indices 0 and 2 return true, because the question mark occurs at position 2. Similarly, we can come up with other test cases that we will be using in the slides that follow. Suppose that we have implemented the program in the following way, wherein the for loop is problematic and buggy because the variable j ranges over 0 to k minus 1 instead of k. And that's why this program will fail in the first test case where the question mark occurs as the last character of the string. By applying a source code level generate and validate APR technique, one might get the following patches among others. The one on the left rectifies the for loop guard condition, while the one on the right replaces the method call with a constant. Both of these patches happen to pass all the test cases, while a human programmer can easily argue that the patch on the right is a correct fix for the bug, while the one on the right simply passes the test cases. We know that manual analysis of these patches could be time-consuming, as they are not only one or two. ObjSim alleviates manual inspection costs by prioritizing patches that are more likely to be correct. For example, the second test case highlighted in the table below, which originally passed, results in the following system state snapshots that are marked in the slides. As you can see from the states, the state for the good fix is identical to the original program, to that of the original program, while for the bad fix, the value of variable j is different, which is a red flag indicating a dramatic change in the behavior of the program on an originally passing test case. Therefore, ObjSim prioritizes the patch on the left over the one on the right before reporting to the user. Now let's look into the engineering details of the system. The tool starts by obtaining bytecode class files for the patch class by compiling the patches. It then instruments the class files so that when we run the covering test cases on the patches, we can collect the system state snapshots at the exit points of the patch method. The result is a set of object graphs, each of which correspond to a particular system state. A hypothetical pair of object graphs is depicted here. In order to calculate the similarity between the system states, ObjSim does DFS traversal over the object graphs and compares field values in a recursive manner. The computed similarity dually distance values are then used to useful patch prioritization. In summary, a score is assigned for each patch, and the patches are ordered based on their scores. ObjSim is publicly available on GitHub. It comes in the form of a Maven plugin, so it is easily applicable for any Maven-based project. Therefore, once you apply an APR tool on a project in one way or another, you can always configure ObjSim to post-process its fix report. An important feature of ObjSim is that it is JVM language agnostic, as it depends solely on the runtime information rather than the program text. Thank you. If you have questions, I'm here to take your questions.
Thanks a lot, Ali, for the talk. I will let anybody who has questions send them on Slack. I see someone typing, so let's just wait a second or two. Just as a general note, while the talk is going on, please keep typing your questions. We don't have to wait till the end. Still have a couple of seconds to wait for the incoming question. So question from Nazareno is, the similarity that you measure, is it that there are no equal field values? Is that what you're measuring? And if so, what about reference-based fields? How are you handling those?
For the reference-based fields, we do it in a recursive manner. If you have a field of primitive type, if they are equal, you assign a distance of 0. If they are not equal, you assign a distance of 1. Okay. So if they are reference, you recursively dive into the object and do it in the same way. Okay,
thanks. I think that there are more questions, but please go on Slack
sure.
And follow up. Thanks a lot, Ali, for the talk. So moving on now, the next talk is going to be, it's a pre-recorded video. It's ProFL, a fault localization framework for Prolog.
Good afternoon, everybody. My name is George, and today I will be presenting a tool called ProFL. So the motivation behind this tool is that in the field of software testing, there seems to be research on fault localization, but only on imperative languages. So the research ignores declarative languages like Prolog. This is partly because fault localization is already a difficult task, and trying to perform it on a declarative language just makes it more difficult. So what is fault localization? Fault localization is just the automation of the process of locating which line, function, or class is responsible for a bug. So the goal of fault localization is not to fix a bug, but rather to suggest lines of code that might be responsible for that bug. So the difference between an imperative and a declarative language is that an imperative language lists out how to get what you want step by step, whereas a declarative language just kind of tells you what you want, right? So Prolog is not executed procedurally. So Prolog works by the system reading in the program and the statements that you declare and then storing it in what they call a knowledge base. Then the user will type a series of queries, which the system will try to answer based on the knowledge base. Sweet Prolog is the most commonly used environment for building and executing Prolog models, and it has this nice library called PL Unit, which allows you to run unit tests with Prolog, which is what we leverage with our tool. So our tool is divided into 4 components, right? The coverage engine, mutation engine, and 2 fault localization techniques. So I'm going to step through each one of these. So the coverage engine, in Prolog, there's no native way to determine test coverage, which is an integral part in fault localization. So what we did is we based our coverage technique on a recent paper which uses mutations to determine test coverage. So first, we invoke the mutation engine to get all the valid mutants of the program. And then for every mutant, we execute the test suite, and we see if any of the test results change. If a test changes, then we conclude that that statement that was mutated is covered by that test. The mutation engine finds all the valid mutants of the Prolog model. So there are certain mutations that don't change the meaning of a program, and also there are mutations that might cause a program to crash or create an infinite loop, so we watch out for that in the mutation engine. Our first fault localization technique is a combination of spectrum-based fault localization techniques, and these techniques use test cases, pass and fail results, and the coverage information of those tests to calculate a suspiciousness value. So these formulas for each statement weigh the total number of failed tests that cover that statement, and also the ratio of passing and failing tests that cover that statement, and then come up with the suspiciousness value. The higher the suspiciousness value, the more likely the line is to be the source of the bug. Our last fault localization technique is a mutation-based technique, and it's based on 2 assumptions, right? So if you mutate a faulty statement, the probability that the mutation causes a previously failing test to pass is higher than mutating a correct statement. This is because mutating a faulty statement sometimes fixes the program. If you mutate a correct statement, the probability of that mutation to cause a previously passing test to fail is higher than when mutating a faulty statement. This is because mutating correct statements introduces new faults into the program. So if you were to run ProFL, this is the output you would get. You get 4 tables, each one representing the result of one of the techniques. You can set an argument so the ProFL only executes the spectrum-based or the mutation-based techniques, or both. If you choose spectrum-based, you can choose which spectrum-based formula it uses. So these are the results of the experiments we performed on 10 Prolog models, and the table shows the number of lines and tests that each of the model has and the runtime of our tool on these models. And then we see the ranking of the faulty statements. The numbers mean the place in which the faulty statement was ranked in terms of suspiciousness value. So even though we allow the option to use one or both techniques, we recommend using both the spectrum-based and the mutation-based techniques, as one technique might be more accurate than another depending on the test case. So one of the things we want to do for our future work is to improve our coverage engine, because it sometimes gives us false negatives. And also we want to test our tool against larger Prolog models. So I'm having some issues connecting to the Slack and getting the Zoom link to present and answer questions. So what I'm going to do is take some of the questions that some of the reviewers of the paper asked and see if I can clear up any misunderstandings about ProFL. So the first question is, does the mutation engine change constants? So we based our mutation engine on a paper that went through and synthesized which types of mutations are sensible for Prolog. So a sensible mutation can be described as a mutation that changes the meaning of a program and does not cause it to crash. And a non-sensible mutation would either not change the meaning of a model or cause a crash or cause an infinite loop. So according to the paper, changing a constant to a variable or a variable to a constant does not change the meaning of the program. Does change the meaning of the program. Therefore, it is considered sensible. Therefore, we implemented it. So the second question is, what happens if the cause of the error is not an existing clause, but rather a missing one? So this is a really good question, and I think it's a bigger problem than just our tool. So I think in general, fault localization techniques are really good at work really well when the cause of the error is a statement that causes a fault in the logic of the program, therefore causing the test to fail. And it does not do well when the cause of the error is some missing logic within the program. So it's definitely something that fault localization techniques need to address. And lastly, discuss how the tool will fare when scaling up to larger programs. So that's hard to say because we had a really hard time finding bigger Prolog models, more complex ones that had accompanying test suites. But one of the things we can say for sure is that the runtime will be significantly higher. That's something we notice even with our test models, is that adding just a few tests exponentially increase the runtime. So that's something to watch out for. But as far as how to do, as far as accuracy, it's hard to say. And yeah, thanks everybody for listening in.
Okay, I guess that's all we will do for that particular presentation. We thank the presenters for preparing that video. Do I have a presenter for the next paper, Tao Judd, Test Augmentation of Machine Learning in Judicial Documents? Okay, I don't think I have them. I didn't hear from them before, and I don't hear from them now. So what I will do is move on to the next talk, which is the last one for the session. It's on test recommendation system based on slicing coverage filtering. Rushian will present that talk.
Okay, can you hear my voice and see my video?
I can hear your voice, but I don't see your video.
Okay, okay, can you see my screen properly?
Yes, I can see your screen.
Okay, let's begin. Hello, ladies and gentlemen. I'm Rui Xiangqian from Nanjing University. It's my great honor to make a brief presentation for number 2 here. My presentation will contain 3 parts. First of all, I will make a brief introduction about the background of the tool, and then the underlying techniques of TSS, also known as our tool, will be proposed. And finally, I will give out several future works as a summary of today's presentation. Unit testing is an important approach of software testing. However, it is not easy for a test novice to write a unit test case properly at the very beginning, since it requires a comprehensive understanding of the production code. So it requires lots of practicing and working experience. According to the State of Testing 2019 reported by Practest, about 65% of the participants will learn software testing through test units, and about 56% will learn through the test book, and more than 40% will learn through a certification in the courses. So through these statistics, we can see that the practice is the main approach of software testing learning, while book and courses are also good choices since they are systematic and reliable. So, however, learn through a book on a course is relatively time-consuming and sometimes tedious, while practice blindly is not that reliable. So, how to combine practice and systematic together is a problem, and how to help test novices gain test design effectively and efficiently it is what we're considering. So we propose TSS. TSS is the abbreviation of Test Snippet Recommendation System. It is mainly composed of 2 parts. First of all, a test snippet corpus, which is constructed offline, and then a test recommendation component, which can recommend test snippets online interactively. To get test scripts with high quality, we collaborated with mock tests. Mock tests have been devoted to software testing and its education in the recent years, and has accumulated lots of excellent test scripts through holding national software testing competition. And we use a program slicing technique to slice the test script on the left to the test snippet on the right, which is more lightweight and more readable. And we treat each unit assert statement as a program slicing point and perform backward slice on each test script. Then we use OpenClover to associate the coverage information between combine the coverage information of every test snippet and get the prepared snippets. We saved these snippets into the corpus and waiting for recommendation. The test recommendation process is finished online. When users submit their test script to finish some test task, TSS will compute the coverage information about the submitted test script, also using the OpenClover, and then this information will be saved into database and for further recommendation judgment. We make a standard. We set a standard for judgment. That is, a test novice must submit at least once, and then score cannot be 0. If the judgment result is false, TSS will do nothing and keep on monitoring, or it will firstly draw several test snippets from the corpus to match the signature of the method on the task on the test, and then we further compute the Jaka distance between the recommended test snippets with submitted test script and recommend the top 2 test snippets to users. And that's all for the recommendation process. There are 2 main works we want to do in the future. First of all, we want to enlarge the test snippet corpus, which is relatively easy because it is constructed offline. We can enlarge the test corpus by simply performing program slicing technique on more test scripts, but it also has some problems we need to handle. And secondly, we want to further complete the recommendation mechanism. At present, TSS only supports the recommendation with Jaka distance and the coverage information. We want to make the recommendation strategy more diverse by supporting more testing metrics like mutation coverage or something else. Yeah, that's all for today's presentation. Thank you. Any questions?
Thanks a lot for the talk. I don't see any. I think somebody is finally typing a question about the talk. The question is from Milosh is, why did you choose OpenClover?
Why I choose OpenClover? Because this tool, our laboratory is using this tool for a long time, and I think this is stable, and we can get the information we want. So we choose it.
But okay, but you don't think that alternative tools may have different solutions or different coverage measurements?
Excuse me.
Is there a thought about comparing it with other tools, other comparative tools? Do you plan to do that, to compare OpenClover, your use of OpenClover? Will your results be the same if you try other tools?
I think it's a good direction, but we will try it in the future. Yeah. Okay.
Well,
thanks for the question.
Thanks for the talk. Thanks for all the questions that we got during the session. I want to just maybe clap for all the presenters on behalf of everyone who attended this session. Thank you all for your great talks. It's well appreciated. So this is the end of the last session for ISSTA 2020. I want to thank everyone who attended and made all of this possible. Thank you all for participating. I think this is then the end of ISSTA 2020. See you next year.